Welcome. This is a video on the derivatives involving logarithmic functions. Now, a lot of people hate logarithms in pre-calculus. They could be a pain, but they're not too bad once you get used to the rules. And a lot of people wonder, well, what's the use of logarithms? It turns out that logarithmic functions have a wide variety of applications in science, and such as in the study of sound, earthquakes, the brightness of stars, pH balance from chemistry, and radioactive decay. So logarithmic functions and their derivatives are actually really important. The derivatives can be important because if you're modeling something in the real world that has a logarithmic function, sometimes you want to know the rate of change of that logarithmic function, which is basically the slope at any point in time. And so the derivative allows you to find that slope, and that's important because it can be useful in science. Of course, we're just going to be focusing on the mechanics of the math of finding derivatives, but suffice it to say they do have a lot of applications, so they are very useful. Okay, so let's jump into the math. Okay, and we're going to need some rules, but not a whole lot of them. Hopefully a lot of this will be a review of Calculus 1. Some of you might have already seen the derivative of logarithms before, but they are very important, so we're going to do quite a few examples. So example, find the derivative of y with respect to x. Find the derivative of y with respect to x. Okay? Or sometimes they'll just say find the derivative, because everyone understands that it's the derivative with respect to x. Okay, so for our first one, we're going to start with a relatively easy problem. So problem number 1. We want to find the derivative of y equals 2 times ln of 16x. Now, ln means the natural logarithm. Hopefully you remember that from pre-calculus. And so this is 2 times the natural logarithm of 16x. Natural logarithm of 16x is an example of a logarithmic function. This is a logarithmic function here. And like I said, they have a lot of applications, but we're going to be focusing on how to take the derivative of them. So here, we're going to need a rule, and it's a pretty simple rule. And the rule is the derivative of a natural log. Okay, so this is a derivative rule for natural logs. So it turns out that d dx of ln of x, so the derivative of natural log of x, is equal to 1 over x. Okay? The derivative of ln of x is equal to 1 over x. So it's a very simple derivative. So if you have ln of something, the derivative of that is 1 over that something. And then, of course, if what's in the inside of the logarithm is more complicated than just x, you're also going to have to use the chain rule. So, for example, the derivative of ln of u would be 1 over u times u prime. Okay? So like here, remember when you have a derivative and you have a constant, the constant basically just stays there, and you just take the derivative of the function. So the 2 is going to stay out front, and we take the derivative of ln of 16x. So we're going to have to use the chain rule here. So dy dx is going to be 2 times 1 over 16x So another way of thinking of this is with the chain rule. Instead of thinking of it as ln of x, we can think of it as ln of u, where u is a function of x. And so that's going to give us 1 over u, but then we have to use the chain rule, so it's going to be 1 over u times u prime. Okay, so 1 over u times the derivative of u. But hopefully you remember the chain rule from Calculus 1. Okay, so here our u is actually going to be the 16x. This is u. Okay, so we got 1 over u there, and then we have to multiply times u prime. So what is the derivative of u? Well, the derivative of 16x is just 16. Because remember, the derivative of a constant times just the variable by itself, the variable goes away, and you just get the constant. So this is going to be times 16. Okay? And then, of course, you want to just simplify this a little bit. Remember, this 16 and the 2 are both in the numerator. They're on the top. So the 16s are going to cancel out here. So we really just have 2 times 1 over x, which is going to be the same as 2 over x. So we have dy dx equals 2 over x. And that's our answer. Okay. And we're starting with an easy one, because some people might not remember everything from Calculus 1. And then we're gonna work our way through harder and harder examples to make sure we can take the derivative of any kind of expression involving logarithmic functions. Okay, so that was problem number 1. And we're mostly going to be focusing on natural logarithms, ln, but we will also later on do a couple examples of other kinds of logarithms, you know, log base 2, log base 5, that kind of thing. But natural logarithms are the most common, and they're used a lot in science. So we're going to be focusing on those. Okay, so problem number 2. Problem number 2 is y equals ln of t to the 4th. Y equals ln of t to the 4th. So here, once again, we have a composite function. The outside function is ln. The inside function is a power function, t to the 4th. Now this one's actually, we're finding the derivative with respect to t. So let me just change it in our instructions. Find the derivative with respect to t. I'm just going to write WRT. That means with respect to t. So here our independent variable is now t instead of x. Okay, so once again we have a composite function. Our inner function is going to be our u. So here u is going to be t to the 4th. So we take the derivative of the outer function, inner function left alone. So some people call the chain rule the outer inner rule, because you take the derivative of the outer function, inner left alone, and then you multiply that times the derivative of the inner function. So for this outer function, the derivative of ln is going to be 1 over, okay, so we're going to have 1 over t to the 4th, and then we multiply this times the derivative of the inner function, which is our u. So the derivative of t to the 4th, here we're going to be using the power rule. So we go ahead and we bring the exponent out front. So we bring the 4 out front. And then we decrease the exponent by 1. So we do 4 minus 1 is 3 is our new exponent. So here our u prime is going to be 4t cubed. So again, we're just using this rule up here that I wrote down. The derivative of ln of u equals 1 over u times u prime. So here our u was t to the 4th. And so our derivative was 1 over u times u prime. So 1 over t to the fourth times 4t cubed. Okay, and remember the 4t cubed is actually in the numerator, so we can cancel some stuff out here. So what we've got here is in the numerator we have 4t cubed, and in the denominator we have t to the fourth. So remember, when you're dividing exponentials that have the same base, these are both in t, we can actually subtract the exponents. Okay? And you want to subtract the exponents wherever the larger exponent is, and you leave it there. So like here, the larger exponent is 4, and that's on the bottom. So we're going to be subtracting 4 minus 3 in the exponent on the bottom. Okay, so what we got here is on the top we still have a 4, and then on the bottom we have t to the 4 minus 3. Because when you're dividing exponentials with the same base, you subtract the exponents, and you do that subtraction wherever the larger exponent is. Here, the larger exponent's on the bottom, so we're subtracting the exponents on the bottom. Okay, and then 4 minus 3 is just 1. So we actually just get 4 over t to the 1. But of course, we don't need to write t to the 1. We're just going to write t instead. So our dy dt is going to be 4 over t. Okay? And remember, it's dy dt because our independent variable here happened to be t instead of x. But they're just letters. T works the same as x. It's just a different letter that represents an independent variable. Okay, so dy dt equals 4 over t, and that's our answer. All right. Now I'm going to assume that some people need a review of Calculus 1. So I'm going to go ahead and try to do as many examples as possible here so that you guys can see kind of a review of Calculus 1 as we work through all the different derivatives of logarithms problems, because a lot of these have lots of tricks that you should have learned in Calculus 1, but some people might not remember for whatever reason. So hopefully this will refresh your memory as we work through these problems. So problem number 3, we have y equals 6 times ln of 10 over x. Y equals 6 times ln of 10 over x. So what's new about this one is we actually have an x in the denominator inside of the function. But we're still going to be using the chain rule. Okay? So using the chain rule, taking the derivative of the outer function, inner left alone, and leaving this constant of 6 out front. So we leave the 6 out front, and then we have 6 times 1 over the inner function, because the derivative of ln is 1 over the inner function. So that's going to be 1 over 10 over x. Okay? So there's our 1 over u. And then we have to go ahead and multiply this times u prime. Okay, so over here, let's work out what u prime is. So once again, our u is the inner function. So here u is 10 over x. So if u equals 10 over x, then how do we find u prime? How do we find the derivative of 10 over x? Well, basically, the trick was, instead of writing it as 10 over x, you actually move the x to the numerator. But when you do that, it gets a negative exponent. Okay, so instead of writing it as 10 over x, you write it as 10 times x to the negative 1. Because whenever you move over the division bar, it changes the sign of the exponent. Okay, so now we can take the derivative using the power rule. So the derivative of 10x to the negative 1, well, we bring the exponent out front, and we decrease it by 1. Okay, so bringing the exponent out front, we have 10 times negative 1 times x to the negative 2. So all I did there was the power rule. I just brought the negative 1 out front, and then I subtracted 1 from the exponent, so it became negative 2. So we actually get 10 times negative 1x to the negative 2. And then we can simplify this. Okay, so we can rewrite this as negative 10 over moving this negative exponent back to the bottom. It's going to become a positive exponent of x squared. So u prime is actually going to equal negative 10 over x squared. Okay, so that's what we've got here. Negative 10 over x squared for our u prime. So that's going to be our 1 over u times u prime. And then, of course, we still have the 6 out front over here. Okay, cool. And you can't leave it like this. You need to simplify it. So remember, if you're doing 1 over 10 over x, that's the reciprocal. So that just means you flip it over. Okay, so if I flip over the 10 over x, what am I going to get? Well, I'm going to have 6 times x over 10 times negative 10 over x squared. Okay? And then the 10s are going to cancel out. And then remember, this x up here is actually the same as x to the 1. They don't write the exponent, it's automatically 1. Okay? And then when you're dividing exponentials with the same base, you subtract the exponent wherever the larger exponent is. So here, once again, the larger exponent's on the bottom, which is 2. So we're going to be doing 2 minus 1 on the bottom for the exponent. Okay, so what's that going to give us? Well, I can go ahead and bring the negative out front. So we have negative 6 times 1 over x to the 2 minus 1. Okay? So I went ahead and brought the negative out front, and then I subtracted the exponents down on the bottom. Okay, and then we can go ahead and move this 6 up to the numerator, because remember, when it's in the middle here, it's actually in the numerator. And I'll leave the negative out front. So we're going to have negative 6 over x to the 1. But remember, 2 minus 1 is 1, and if your exponent is 1, you don't write it in your answer. So our answer is actually just going to be negative 6 over x. Okay, and that's our dy dx, the derivative of y with respect to x. Okay, cool. So I wanted to get to some trickier ones, because this is mostly review of Calculus 1, but we're kind of applying it, the stuff from Calculus 1, to the new stuff in Calculus 2. But really the only new thing we learned here is the derivative of ln. But all the tricks that you hopefully remember from Calculus 1 are still useful in Calculus 2 and Calculus 3 and forever, really. So let's see another example. So problem number 4 is going to be y equals t times a quantity ln of 7t quantity squared. Okay, y equals t times a quantity ln of 7t quantity squared. So here you have to kind of remember some stuff from Calculus 1 and apply it here. So we have a composite function there, and we also have two functions multiplied together. So what we're going to be using here is, since we have two functions multiplied together, we're going to use the product rule. So hopefully you remember the product rule from Calculus 1, but of course if you don't, that's why I'm putting it here, so you can get your review in this lecture. So the product rule says that the derivative of two things multiplied together, so the derivative of u times v is equal to u v prime plus u prime v. So uv quantity prime is equal to u times v prime plus u prime times v. I know my primes look a little bit like ones there, so let me fix that. Okay, so here we can just label these two things multiplied together, and then we can work things out and do the product rule. So here our u is going to be t, and then our v is going to be this big thing here. So our v is actually going to be the quantity ln of 7t quantity squared. So what's usually recommended is somewhere over on the side, you work out what u prime and v prime are, and then you plug them all in to the product rule. Okay? So we know that u is t, so that means u prime is just going to be 1. Because remember, the derivative of your independent variable is just 1. Okay, so u prime is 1, that's easy. Now v prime is a bit harder. So over here, let's do v prime. So now for v prime, we have a composite function. Actually, we have a double composite function. So we have an outer function, which is a square function. Then we have a middle function, which is ln. And then we have an inner function, which is 7t. So it's really 3 functions in 1. So we're going to be using the chain rule, working from the outside inward. So starting with the outside function, which is the square, we're going to go ahead and bring the 2 out front using the power rule. Okay, in fact, let me do this one in a different color. So I'm going to bring the 2 out front using the power rule, and I decrease it by 1. Okay? So I'm going to have 2 times ln of 7t. So we're going to have 2 times ln of 7t raised to the first power, right? Because taking the derivative of the outer function, which is a squared power, the second power, we bring the 2 out front and then we decrease the exponent by 1, so it becomes 1. But we don't need this 1 here, because any number to the 1 is just a number. So we're just going to write it as 2 times ln of 7t. So that's the derivative of the outermost function. So that takes care of the power. And now we go to the middle function, which is ln. So the derivative of ln of 7t is going to be 1 over 7t. So the next thing we have here is times 1 over 7t. And finally, we multiply this times the derivative of the inner function. So what's the derivative of 7 times t? Well, that's just going to be 7. The t goes away, so we just get 7. Okay, so this whole thing is going to be multiplied times 7. Okay, and then stuff is going to cancel out here. So the 7's cancel out. And so what we're left with is actually, on the top we have 2 ln of 7t. And then on the bottom we have a t left over. So our v prime is going to be 2 ln of 7t all over t. Okay, so we got our u prime and we got our v prime. So now we can just plug everything in here. So seeing the product rule here, we have, let me zoom out a little bit. We've got our product rule. It's u v prime plus u prime v. Well, we know u is t, v is this thing, u prime is 1, and v prime is this thing. Okay, so what we're going to do is just plug everything in. So what we got is u v prime, so that's going to be t times v prime, which is this whole business over here. So 2 ln of 7t all over t. So we're going to have t times 2 ln of 7t all over t. That's our u v prime. And then we have plus u prime v. So u prime, we said, was just 1. So this is going to be plus 1 times v. And v was what we started with over here. So that's going to be the ln of 7t quantity squared. Okay? And you do want to simplify this a little bit. In particular, you'll notice that there's a t on the top and on the bottom for the first term. So we can go ahead and cancel out those t's. And then after we do that, we're pretty much done here. So we've got, since our independent variable is t, we've got dy dt equals 2 ln of 7t plus, well, 1 times any number is the number, so we don't need that. So we're just going to have plus the quantity ln of 7t quantity squared. So that's it for that problem. So that's going to be our answer, 2 ln of 7t plus the quantity ln of 7t quantity squared.